Hello, everyone. On today's Wolfram live stream, we have Sandra Lindblom, and she'll be talking about causality from a philosophical and historical perspective and how it applies to the Wolfram Physics Project. Sandra, go ahead.
Great.
Sandra, thank you so much for having me. I'm a PhD student in philosophy at Cambridge, where I'm writing a dissertation about the Scottish philosopher Lady Mary Shepard and her alternative theory of causality in physics. In this talk, I'm going to present what I've learned from the research of my PhD, and then I'm going to talk about how it connects to the physics project, which I studied at the winter school. Since Shepard presented her view of causality as an alternative to the dominant linear view of causation that still dominates today, which originates from Hume, I'm going to start by briefly summarizing how she read his philosophy of causation and then show how she departs from it. Then I'm going to talk about how Shepard's alternative theory relates to the physics project, and I'm going to show how I've been formally and computationally expressing her theory in alternative causal graphs to the current ones used in the physics project. Okay, so I'm going to share a screen now, which is a list of quotes that I'm going to be appealing to when I'm talking. So starting with Hume then. So can everyone see that? So Hume, he was a famous Scottish philosopher, famous for his book, A Treatise of Human Nature. And he was interested in many philosophical questions, one of which was the metaphysics of causation. There's no question, he wrote, which on account of its importance as well as difficulty has caused more disputes both among ancient and modern philosophers than this concerning that quality which makes causes be followed by their effects. End of quote. Causation and the question of how its two components, cause and effect, relate to one another has been one of the most important but also most difficult questions in philosophy since antiquity, in both Western and Eastern traditions. For instance, to Plato, causation plays such a central role that he has one of his characters in The Sophist argue that the power to cause or to be caused is what it means to exist. Here's a quote from Plato. He said, "Everything which possesses any power of any kind, either to produce a change in anything or to be affected, even in the least degree, by the slightest cause, has real existence." End of quote. In the Physics, Aristotle argued that knowledge is inseparable from knowledge of causes. We don't even, quote, know a thing until we are acquainted with its primary causes, end of quote, according to Aristotle. We find similar ideas in Arabic philosophy as well in the Middle Ages, where Aristotelian ideas exerted a significant influence. We also find that this question of how to explain the connection between a cause and effect has been one of the most important disputes between the two dominant Indian philosophical traditions since antiquity. So in philosophy, science, and everyday life, we cannot but use causal terms. The language of causing, creating, making, producing, generating, etc. The British philosopher Bertrand Russell, however, famously called for causality to be banished from our vocabulary because he thought it was, quote, a relic of a bygone age, surviving like the monarchy only because it's erroneously supposed to do no harm, end of quote. But not even Russell managed to follow his own decree. His writings are filled with the language of causality. So causality is undoubtedly fundamental to our conception of reality. But one central question that has arisen in the history of philosophy is, does causality exist as a category of the real world, or is it something in our minds that we project onto the world? Perhaps a superstition, as Wittgenstein proclaimed it to be. So Hume, as I mentioned, was deeply interested in causation. In Hume's major work, A Treatise of Human Nature, he describes his search for a theory of causality that was clear and intelligible, only to be disappointed to find theories that he described as perfectly unintelligible and inexplicable. Similarly, Immanuel Kant tirelessly wrestled with understanding what causality is, describing his longing for the day when it would be clearly explained. He wrote, "How can I understand the circumstance that because something is, something else is to be? I would very much like to have this made clear to me," he wrote. What both Hume and Kant found puzzling about our common concept of causation is that it entails a necessity. When you say that there's a causal relation between two things or events, it seemed to entail that if one thing occurs, another thing must also occur. There's no cause without an effect, and no effect without a cause. But what reality, if any, answers to that kind of a relation? That's a very strong relation, it's a necessary one. So when we look at Hume's writings, every time he gives examples of what he calls causes and effects, they're always examples of events that occur separately in time. For example, he takes the example of billiard balls moving across time, the time it takes to nourish the body, the time that passes between taking a medicine and falling asleep. So as Hume saw it, there's a time difference between what we call the cause and the effect, such that he said there's a priority of time in the cause before the effect. So we see this is the first quote on the handout. Priority of time, the cause before the effect. And one of his examples here is of a billiard ball. So he says, when I see, for instance, a billiard ball moving in a straight line towards another, even suppose motion in the second ball should be, by accident, be suggested to me as the result of their contact or impulse, may I not conceive that 100 different events might as well follow from the cause? So the idea here is he's implicitly assuming that the cause would be the first billiard ball moving, and then the effect would be another billiard ball changing its motion. And there's a time difference between those two events. So for Hume, cause and effect is about how something in the past is connected to something else that falls in the future. It's about how we anticipate what will happen in the future based on what's happened in the past. So another way to put this is a linear, temporally separate, and one-directional view of causation. This means that it sees cause and effect as one event that happens after another in a one-directional arrow from the past to the future, so from the cause to the effect. And while a cause affects its effect, the effect does not also affect its cause on this definition, because then the effect would have to occur before its cause. So on this linear view, there's nothing mutual or cyclical about causal relations. The line of causal influence is one-directional. And with this linear, temporally separate, one-directional definition of cause and effect, many read Hume to be arguing that nothing in our experiences of the world grounds a necessary connection between a cause and effect, so between these temporally separated one-directional events. All we see is that one event does follow another time. We never see that it must do so. So famous quote from Hume we have is the third one. He says, "In reality, there's no part of matter that does ever give us ground to imagine that it could be followed by any other object in the future." Actually, these we don't need, I just realized. Okay. So on a more traditional metaphysical reading of Hume, he rejects the existence of causation as a necessary connection and holds that, according to him, there's nothing that necessarily binds anything together. All that exists in the physical universe are inconstant objects standing in inconstant relations to one another, with the possibility of unpredictably changing at any moment. Indeed, he does write that objects are in their nature changeable and inconstant. Okay, so this is in the 1700s. If we move now to contemporary metaphysics, theories of causation generally share Hume's assumption that cause and effect, at least most of the time, follow each other in time. That is, that they're linear and asynchronous, and also that they're one-directional. The cause causes its effect only. Even contemporary theories that diverge from Hume in some respects nonetheless tend to assume that he was right about causal interaction following this linear one-directional pattern. There are some philosophers who've argued that effects can come before their causes, which is also a linear, temporally separate and one-directional view of causation, whereby one event occurs before another, just in reverse. But that causes come before their effects, at least most of the time, is the dominant view in philosophy today.
I have a
So as
question on the third point from Hume.
yeah,
So
but
he's saying that like you have an object and the fact that it stays like the same is sort of arbitrary, or that it doesn't have to be so.
the idea is something like if you take the billiard ball example, so if you meant like one billiard ball moving before it collides with another billiard ball and then the second billiard ball starts moving. So as he sees it, the cause of the second billiard ball's change in momentum would be the first billiard ball moving. And there's a time difference between these events. Like the first billiard ball was moving and then the second one started moving. And so his idea here is that he thinks that there's nothing like when you just see the first event, when you just see the first billiard ball moving, there's nothing that shows that that event must be followed by the second billiard ball later starting to move. Like lots of things could happen in between, like maybe the first billiard ball never ends up hitting the second billiard ball, like maybe the lamp above the pool table falls down. And so he's saying that there's not like a necessity in that, like the cause is always followed by this effect. So like whenever you have a time difference, like there's something in the past connected to the future, there's always something that can intervene or prevent the effect from occurring, because he has these that they're separate in time. Does that make sense?
Yeah, that makes more sense. Yeah. So I mean, you have like these two instances of time, and you have these two states of this of a system, and in between those temporal like states is like the forward propagation in time of you know physics and motion and all these things colliding as the case may be, and eventually if the things do collide, then there will be like a cause event for the second billiard ball to gain motion,
Exactly.
barring like something happening in between those two time steps.
Yeah, exactly. Um, that's a really good way to put it. And so this is what leads him famously to his skepticism. He's known of this skepticism to causation, because what he's saying that, well, but between any two temporal states, uh, there's no like certainty that they will be followed by each other. Like something could happen in between that prevents the second one from occurring. Um, yeah. So
Right,
so
conceivably.
this is
Yeah, so like I guess it's difficult to conjecture a universal like philosophical law saying, "Oh, if I see something traveling this way in a billiard ball, and then this billiard ball is gonna always happen to move as a result." Not the case, because other intervening events can conceptually be applied in between.
exactly. Yeah, exactly. So this is Hume's picture, and this is um and as we're gonna see soon, uh the philosopher that I'm writing about, Shepard, she found it difficult to see how this linear, uh temporally separate one directional view of causation, how that can explain uh some phenomena in physics, such as Newton's third law, which is nonlinear, synchronous, and bidirectional. Like whenever a body exerts a force on another, that body is synchronously acted upon by an equal opposite force. I'm going to talk about um, that later. Um, but just now, it's important to see that. Um, so Hume's linear view has not only significantly influenced metaphysics in general, it's also been popularized in science. And I'm going to talk later about how we see this, for example, in the physics project. But so before the dawn of quantum mechanics in the early 20th century, science generally endorsed this linear view of nature where one event causes a later one in a one-directional arrow from the past to the future. But with the rise of quantum mechanics, we've seen how physics has been increasingly challenging the idea that reality can be fully understood from a linear framework, breaking down nature into lines seems to miss important parts of it. Instead, quantum mechanics suggests a much more complex, interconnected, and nonlinear view of nature. Where quantum phenomena such as entanglement seem to suggest that nature is filled not with separable one-way relations, but rather with inseparably connected reciprocal interactions between particles. Okay, so that was a bit of background. Now I'm gonna move to Shepard. So we've seen it's been explored where the causes come before the
Wait,
effect. Oh yeah, yeah, go ahead.
before we move, like you mentioned that it's like linearity of causality was before quantum mechanics, right? But well, certainly there's like there's some mention in philosophy that the event could be caused by multiple events, right? So that it's not necessarily linear, even before quantum mechanics. It's like, right? So that the event has to be preceded by two events in order to be caused, right? So
Yeah, that's right, but that it would still be this view that the cause, even if it's multiple causes, comes before the effect. And so you still get this like sequential view. Am I understanding you correct? That it's still that these events happen first and then later we get some effect.
It's directional, yeah.
yeah, it's just directional, it's sequential. I would kind of disambiguate those two terms. It's like for me, sequence is just like a path from one event to another as a linear path, right? But when it doesn't have to be just directional, it can be a little bit more complicated, like intertwined between those, like multiple events causing one event and the whole graph of events. That would be still directional, but not sequential.
So yeah, I should disentangle those. Yeah, um, so it's been explored the idea that causes come before their effects, and where the effects can come before the causes. But in my research, I focused on a very unknown philosopher who took neither standpoint, who neither thought that causes come before their effects, nor that effects can come before their causes. According to Shepard, who published an anonymous pamphlet about causation in 1824, cause and effect are synchronous. And she also argues that the relation between a cause and effect is a mutual relation. She says, that qualities play on each other as a mutual cause and effect. According to Shepard, causes and effects stand in quote, equal mutual relations. Quote. Mutuality and synchronicity appear to be two central features of Shepard's view of cause and effect in nature. She writes that the manner of efficient cause is not by arbitrary antecedency and subsequency of events, so like one event occurring before another, but by mutual and simultaneous affections and interactions of particles or qualities. End of quote. In causation, we enter a relation of mutual and synchronous interaction, according to Shepard. The science that Shepard herself deemed most fundamental is physics. She describes the subject as the tree trunk from which all other sciences stem from, like branches. She writes, mathematics is truly but one branch of physics. There is truly but one science, however subdivided afterward. Therefore, in my dissertation, I primarily use examples from physics to illustrate Shepard's view, because I think they're the most clear. Okay, so what is this definition of causation that leads Shepard to conclude that cause and effect are synchronous and mutual? So here I have two quotes, number 4 and 5, where she gives the definition. She says, a cause is such action of an object as shall enable it in conjunction with another to form a new nature. The other quote, she says, the junction of two or more qualities or objects is wanted to every new creation of a new quality. So instead of this sequential and one-directional description of causation as one event followed by another, Shepard, as we can see, is describing causation as a much more complex relation. She thinks it's when two or more things together create a third. She calls each cause a union composed of at least two entities. This is also interesting because traditionally, philosophers have tended to view causation as something different from composition. but to Shepard, these two are closely connected. According to her, whenever anything happens, it's caused by at least two other things mutually interacting or combining. So this is Shepard's general account of causation that she applies to all areas, including both physical and mathematical examples. So a physical example Shepard gives is Newton's second law. Here she writes, quote 6, "No motion would have taken place except from the conjunction of the body and the impulsive force." The idea here is to be the union of a force applied to a mass, and that mass creates an acceleration. You can also think of chemical cases here, like hydrogen, oxygen atoms come together and create a water molecule. So with this alternative definition of causation, Shepard goes on to argue that an effect is something new relative only to the two or more objects that caused it, if you consider those objects separately. She writes, "A cause is such action of an object as shall enable it in conjunction with another to form a new nature, capable of exhibiting qualities varying from those of either of the objects unconjoined." To take a clear example, think of like an H2O molecule is new relative to the hydrogen and the oxygen atoms if you consider them apart from each other. However, Shepard said, the effect is but a different way of looking at the union of those objects which caused it. She says that the union of those two objects is the cause of and is one with the effect. Cool. So thinking of the H2O again, so H2O molecules new relative to the hydrogen and oxygen atoms, when considered apart from each other, but H2O is but a different way of looking at the union of those hydrogen and oxygen atoms that caused it. According to Shepard, this is why there's never a cause without an effect and an effect without a cause. They are but two different ways of looking at the same thing. Shepard also saw this pattern in mathematics, except here, of course, the objects aren't in time and space. She says, well, or this is my example, think of like 12 is different from 7 and 5 if you consider them apart from each other, but 12 is but a different way of looking at the combination 7 plus 5. You can also think of a momentum transference as an example of this. So for a body to change its momentum, there has to be at least one giver and receiver of that quantity of momentum. For instance, in a collision of billiard balls, like one billiard ball gives momentum to another, which causes the second one to change its momentum. So here you could say like the union of two equal and opposite momenta, so the lost momentum, the gained momentum, which are equal, the opposite. And then the effect is the change in the body's momentum. These are just two different ways of looking at the same thing. You're looking at two different sides of the same equation. Therefore, whenever you have one, you have the other. Okay, so with this definition of causation as at least two entities combining to create a third, Shepard argues that cause and effect are best understood as synchronous instead of successive. So here I have two quotes. She says, antecedency and subsequency are immaterial to the proper definition of cause and effect. On the contrary, although an object, in order to act as a cause, must be being antecedent to such action, so like it has to exist before it causes something, but when it acts as a cause, its effects are synchronous with that action. Effects must necessarily be in and with their causes in the very moment of the effect's formation. And another quote, for H says, in their union there exist those newly formed objects or masses of qualities called effects. For in this union, cause and effect are synchronous, and they are but different words for the same essence. An example Shepard gives of this is Newton's first law. On quote 9, she writes, for the proof of this simultaneous action of cause and effect, let the reader reflect that every object would remain as it existed at any given moment unless it were interfered with, and an interference cannot be either before or after itself, but must be in and with the same moment of the change occasioned by it. So if you think of a collision between two billiard balls again, even though the collision occupies a small, finite interval of time, and during that brief time period, one billiard ball momentum is decreasing continuously as the other Billy ball's momentum is increasing continuously. But these two changes are synchronized in the sense of like continuously as one Billy ball is losing momentum, the other one is gaining. So it's not instantaneous, but synchronous. You can also think another good example of this could be gravitational interactions, which Shepard would have had access to, like Newton's description that it's not as if, for example, the sun exerts a force on the Earth, and then at some later time, the Earth keeps orbiting around the sun. Rather, these are synchronous. Okay, so that's the synchronicity. So now I'm going to this idea that there's mutual relationships in causal relations. So when you first read that, you might be thinking, but there's a clear asymmetry to Shepard's account of causation. She's saying whereas a cause is a plurality of entities, so it's these at least two entities coming together to form a union and then producing an effect synchronously. And that effect of that plurality is a singular entity. So as Shepard saw it, when we think of a cause, we think of it as a plurality, whereas when we think of an effect, we think of it as a singularity. So it's not symmetry, clearly, that Shepard's arguing for. However, she does argue that causal interactions involve mutual interactions. She writes, quotes 10 and 11, "The manner of efficient cause is by mutual and simultaneous affections and interactions of particles or qualities. And then all qualities of existing objects play on each other as mutual cause and effect." So more precisely, there seem to be two mutual relationships in each causal relation on Shepard's theory. The first is that an effect arises synchronously out of a mutual and synchronous interaction between at least two entities. So one clear example of this in physics is the giving and receiving of momentum. Think of a body's change in momentum arises synchronously from at least two objects giving and receiving momentum, which involves both of them synchronously and mutually affecting each other's momentum. Like one object is losing momentum, which makes the other one gain that quantity of momentum. Together, the mutual and synchronous interaction between these two different momenta, the gain versus the loss of momentum, creates a change in momentum and therefore a new velocity in both the first and the second object. So a cause is kind of like a square root on Shepard's view. It consists of two values that are numerically the same, but with opposite values. One is negative and the other positive. So by virtue of each of the billiard balls' change in momentum is the synchronous result of two opposite but equal momenta. By virtue of standing in this mutually binding relation, the effect arises. I think Shepard would argue. So the effect is the synchronous result of two or more entities synchronously and mutually affecting each other. The cause and the effect themselves also seem to mutually depend on each other in Shepard's view. So again, if you think of a momentum transference, if no momentum was lost or gained, neither object would have changed its momentum. But it's also true that had neither object changed its momentum, those two objects would not have given and received that quantity of momentum. Momentum transference and momentum change are mutually dependent on each other. They appear to mutually and synchronously cause each other. So when two synchronized equal and opposite momenta, one object's loss, another's gain, together co-create a change in momentum. That change in momentum, the effect, is equal to the combination of those two opposite and equal momenta that caused it. They're equal in magnitude. They're merely two different sides of one and the same equation. You're looking at the same thing in different ways. So giving and receiving momentum is one good example of these two kinds of mutual and synchronous interaction in a causal interaction for Shepard. But her theory is not limited to it or any kind of giving receiving for that matter. like we can also find examples of this in forces. So consider again like the billiard balls. When momentum is given and received between the two billiard balls, two equal and opposite forces arise synchronously, according to Newton's third law, to ensure that the total momentum is conserved. So if you think like that, the first billiard ball pushes the second one into motion, but the second ball also synchronously pushes the first one back into rest. So it stops moving, because otherwise the momentum will not be conserved in this example. So what is new in this case is that the first object stops moving. Another way to put it, the effect is that the net force of the system, due to the interaction between these two objects, becomes zero. Another question could be, what caused the combined system to acquire a net force of zero? Well, it seems that on Shepard's view, it would be the mutual and synchronous interaction between the two objects, equal and opposite forces. So in this case, the two opposite forces between the two billiard balls cancel each other out because they're equal in magnitude but opposite in direction, and so they create a balance. Another way to put it in Shepard's terminology might be this union of two equal and opposite forces created something new, namely a net force of zero in the system. And this net force of zero, the effect, is equal to the combination of the forces within the system that cause the system's net force of zero. They're just two different ways of looking at the same thing. They're two different sides of the same equation. Like to look at the resultant net force of zero is simply to look at the combination of the two opposite forces in a different way. So in summary, it seems like what's unique about causation for Shepard is this idea that it's this mutual relationship between at least two things synchronously affecting each other and synchronously creating something third, which is the effect. And so cases of transferences are only examples of this more general relationship in nature. Another way to...
view, sorry,
Oh, yeah.
it seems like it's very physical and kinetic, I guess, and I like its symmetry. So, but what is the cause in this? There's like an initial setup of you have these two billiard balls like going towards each other, and then you have the effect of they've changed momentum. Maybe one was still, and then they transferred to the other, or they're kind of going in opposite directions, and then they collide and they bounce off. So you could say like, well, here's the effect. They're going in this direction as an output, and the input is like here, and then the cause is like in the middle, where they're like actually touching and interacting and exchanging forces symmetrically.
That's exactly Shepard's view. So what's different with Hume is like instead like that he looks back and looks at like antecedent conditions that, whereas Shepard, she's looking at like when something happens, like that's when the causal interaction takes place. It's like the interface between two events. And so indicate, for example, like if the effect is like the second billiard ball stopped moving, like what caused it to stop moving? Or like what caused an object to change its momentum? She looks at like what is it that synchronously arose when that happened, and that's where she finds that she thinks whenever something happens, there's at least two things synchronously affecting each other, and that in turn synchronously creates something third. So for example, like two equal and opposite forces together create a net force of zero in the system. I mean, not always, but in this specific case.
I have a question about that view. So would she, how would she factor in maybe a single object that is just interacting with time and then changing over time, like evolving without interacting another physical object? Yeah, just how would that work in this case?
Interesting. And I have to think about that. I mean, she talks about that a cause doesn't have to involve like objects. Like she talks about qualities as well. So I suppose like in these cases, she uses something like that the interaction is still like it's still are at least two things involved in the sense, even though it's not an object, like there's one object and then like qualities of time, like features of time, or so I think like she doesn't mean like there has to be a body with mass. Like there has to be at least two bodies with mass. And because as I mentioned briefly, now I'm focused on physics here, but she saw this as a more abstract theory of causality as well, like applying to mathematics. And so these are just like concrete examples of more general view that at least two entities of some sort have to interact, whether
Makes
that's
sense.
like numbers or masses. Or does that make sense?
Yes, okay, great.
Okay, thank you. So another way I think to describe what Shepard seems to be describing is that a cause consists of synchronized opposites that synchronously co-create something new, namely an equal effect. So if you think, for example, a pair of equal and opposite forces, an equal loss and gain of momentum, or the opposite directions of atoms when chemically bonded, or opposite charges, or whatever. These are all examples of oppositions that synchronize, and in that synchronization, they produce synchronously effects, which are but a different way of looking at the union, so at this synchronized polarity that is its cause. For example, a system stops experiencing motion, an object changes momentum, or a molecule is formed, or whatever the effect is. So as Shepard saw it, we need a nonlinear bidirectional framework to fully comprehend the complexity of what's happening in causal interactions. So unlike what Shepard interpreted to be Hume's claim that causal necessity is something that we project onto a world where no tie so strong is to be found, Shepard's view entails that causation, that is, the idea that new things are synchronously co-created when at least two entities synchronously and equally affect one another, or put differently, that it's out of a synchronized polarity that something new is created. This is a discoverable category of the real world, Shepard. So it's not something we're projecting onto the world. This is something we can observe. Okay, so now you might be thinking, okay, so if we zoom in on events enough, maybe we do find these synchronous mutual interactions that Shepard is describing. Like if we're looking at the level of each individual molecule forming, or the exertion of each equal and opposite forces, or the giving and receiving of each quantity of momentum, for example. But what about the temporally separated processes we experience, like the sequence of time that we encounter every day in our observations? Like what we experience is one event happening after another. So we experience things linearly, successively, like one direction, like the arrow of time from past to future. We don't experience this bidirectional and synchronous phenomena that Shepard describes. And so what accounts for that? And what does she say about the sequences that we experience? So I'm going to read first I'll read the two first quotes here where Shepard describes sequence of time, which is number 12 and 13. She writes, some objects determined to the senses will invariably be antecedent to others, but such sequences are only successive effects, she writes. And then she says, cause and effect are synchronous in each step of the series of actions which take place. So what does she mean here? So I think an example to illustrate Shepard's view is a series of billiard ball collisions, as a very concrete, simple example. So if you have a series like billiard ball 1 collides into billiard ball 2, and then billiard ball 2 later collides into 3, and so on and so forth. So it seems that Shepard argued that billiard ball 1's and billiard ball 2's momentum transference caused the second billiard ball's change in momentum. But it didn't cause billiard ball 3's later change in momentum, because those are not synchronized with each other. So billiard ball 3's change in momentum was caused by the momentum transfer between it and billiard ball 2, because only they are exactly synchronized. So what this means that like in a series of events, like where say C1 causes E1 and later another effect E2 arises, E1, so the first effect, cannot be the cause of the second effect if they're separated by a time difference. However, if like the first effect is synchronous with another effect, then the first could be the cause of the second, otherwise not. So in other words, as Shepard saw it, a series of causes and effects is linear, but the series is composed of individual causal interactions which are not linear. So here below we have just an illustration of this idea. So basically whenever there's, in this case it would be collisions that are separated by time, they are not causally related for Shepard. So she wouldn't say, for example, that what's happening between the first and second Bilbo Ball had anything to do with the fourth and the fifth, or nothing causal at least. Okay, so as Shepard saw it, Hume and his followers, their mistake was that they didn't zoom in enough on the sequences of events that we perceive. Here's another quote, number 14. She wrote, "A chain of conjunctions of bodies," so she's thinking like, for example, like a series of billiard ball collisions, of course occupies time. And it's the reason why the careless observation of philosophers, enabling them to take notice of only some one distinct effect, after perhaps innumerable successive conjunctions of bodies, occasions the mistake by which they consider subsequence of effect as part of the essential definition of that term, and priority as essential to the nature of cause. So Shepard writes, quite difficult, but the idea here seems to be just going back to the Bilbo cases, where she thinks this mistake that causes come before effects come from, like where that comes from is that we observe one thing that happens, like let's say we observe like the fourth billiard ball changes momentum, and we then, and instead of connecting that and looking at like what happened in this individual instance, we just like look back, we just zoom out and look at, well, the first billiard ball gave momentum at some earlier time. Where Shepard is thinking, no, there's actually multiple causal interactions happening here, like, and we need to look at each change and what synchronously produced it. So as Shepard saw it, like when we zoom in on the series of changes that we observe, the sequence that we observe, we see that it's composed of these individual changes, each of which involves a synchronous interaction between at least two entities mutually affecting each other, and through that creating something third, something new, the effect. As Shepard saw it, Hume simplified nature to the point of falsity. So, as mentioned, science has largely endorsed Hume's linear, temporally separate, and one-directional view of causation. And we also see it assumed in the causal graphs of the physics project. At the Wolfram Winter School, I therefore worked on expressing Shepard's alternative theory formally to show what her alternative causal graphs would look like. So these like more zoomed-in causal graph. So now I'm going to stop sharing this, and now I'm going to show the graphs I made at the winter school, which I think illustrate this well. So this is when we're zooming out and we're looking at multiple causal interactions. So if we start with, so here we did is if we start with three base entities, call them X, Y, and Z, and they can form the following four different causal interactions. So the first possibility in the top left corner is that Z and Y mutually and synchronously affect each other, which is the arrows going back and forth. And that mutual synchronous interaction synchronously creates A, which is composed of Y, Z. Like A is the union of Y and Z. Or what could happen is that Y mutually interacts with X, and then they together co-create B, which is the union of X and Y. or what could happen is that X mutually interacts with Z, forming what I call C, which is composed of Z and X. Or you could have like a big cause interaction where like X, Y, and Z all mutually interact and produce D effect, which is composed of X, Y, Z. Okay, so this is like just starting with like one cause interaction. But what happens then like after that? So this means that there's, so then I used a multi-way system of these possible causal interactions just to show like that from starting with X, Y, and Z, here are the different possible paths that can occur. But what's different is from like how multi-way systems are typically done at the physics project. It seems like a Shepardian multi-way system would show that like when one causal interaction occurs, it excludes the other ones from occurring. So like of these, we have these 4 different paths. If one of them occurs, like say like if Y interacts with Z, then the other ones can no longer occur. Because, why is that? Well, because if we only have the 3 entities X, Y, and Z, if one of them occurs, then that one is sort of taken, like it, because now it's become the effect, like which is this composition of that one with something else. So of these 4 possible causal interactions, only 3 of them can theoretically become a sequence of 2 steps. So now thinking like we start with one causal interaction, what can happen in a sequence? So only 3 of them, because one of them involved X, Y, and Z. So now there's nothing left to interact with. So we have, there are these possible interactions, and if one of them occurs, it excludes the other ones. So for example, we can have if A occurs, which before it was caused by Y and Z, that means now that A can only interact with X because Y and Z is already taken. It's part of the effect. So, and then if A and X interact, it can create AX. But if this has occurred, now all the base entities are taken. So any other sequence of 2-step can't occur. But if the first one didn't occur, then you can have, for example, that Z interacts with B, which is composed of XY, and create BZ. Or alternatively, if this one didn't occur either, we can have Y interacting with C, which consists of ZX, creating CY. So like one of these sequences occurring excludes the other ones from occurring. So this is a simple illustration with just 3 entities. And so what's interesting to see is first it's interesting how they become, as you see, like bidirectional. And then it's also interesting to see how then when we zoom out and look at sequences, we have like in multi-way systems, we see that like if one path is taken, it excludes other ones from forming. Yeah, so that's what I've been working on. Thank you so much for listening.
Yes, thank you, Sandra. That was very interesting. So in those, can you show the notebook again?
Yeah, of course.
Okay, so what do the arrow mean? The arrows mean exactly? Is that causation?
In these at the start, yeah. So they symbolize like that they're in. So the arrows between, for example, Y and Z, they're showing that like they're mutually interacting with each other, which is why they're going both ways.
Mhm.
It's like Y and Z, and then these arrows they're leading to the effect. So they're showing that here, so the mutual interaction between Y and Z creates A, which is composed of Y, Z.
Yeah, so
That
the
makes
interaction makes the output as AYZ, I guess. Like in my mind, I
exactly.
don't know if I want the arrows to go back from AYZ back to Y and Z. Like I want there to be only directed downwards, but that's just in my head. Just a thought.
Yeah,
maybe.
well, that's the thing that's unique with Shepard is that it goes both ways in that this is synchronous and one like they're both mutually dependent on each other. So in this case, like Z and Y mutually affect each other creates A, but if so A wouldn't have existed unless Y and Z were mutually affecting each other, but Y and Z wouldn't be mutually affecting each other if A didn't come to be either, because these are just two different ways of looking at something. So you could think of, for example, um, like a molecule being formed. If you say
like the existence of
like-
water necessitated the coming together of hydrogen and oxygen.
yeah, exactly. Because like if it hadn't arisen, they wouldn't have chemically bonded in this way. But the chemical bonding also created the molecule. Or also think of these as like two equal and opposite forces. Like, well, if those forces were acting each other, we wouldn't get a net force of 0 in the system. But if the net force of 0 hadn't arisen, we also wouldn't have this mutual interaction. So I think exactly what was unique about this is that it's the interaction that is the cause, that it's an interaction that produces something new. And then the effect also creates that interaction. So like as Shepard saw it, nothing would ever happen if there was just entities in the world. Like it's about these entities interacting in certain ways with each other. That's when change is brought about.
Right, and certainly in physics, everything in physics basically happens locally at when two things meet in space and in time at the same moment to exchange some of their attributes with each other, like momentum, or charge, or the case of molecules or something like that. But it's concurrent and it's equal and opposite, and there are these conservation laws, or there's all this matter and energy sloshing around, and none of it goes away. It just transfers between objects, and so it's a very symmetric relationship, and it's informed from like what happens in physics. That we live in a universe that doesn't randomly do things. That is to say, if we don't live in like a dream world where anything could happen. Like something just doesn't like spawn into existence, like a dragon over there, from like nothing, just because someone like typed it in and said, "Oh, we're in a simulation," hit enter. That we have conservation laws in the physics that dominate our universe.
In my dissertation in the first chapter is gives a background about how also during Shepard's time, so during the early 19th century is really when conservation laws were coming to the forefront of both physics and chemistry, and I think Shepard is definitely drawing upon this and this influence. And I think, like you said, like exchanges are like really clear and probably the most commonplace example of Shepard's view. Like exchanges of momentum or energy or electrons, something this like local, but I don't think her view is limited to transfer cases. Because we can also see it with like forces or something. So I think what's essential for us is just you need at least two things mutually affecting each other, and that synchronously creates something third. But I think different that the exchange cases are the most widespread example of that, really.
Nick, do you have any comments from a quantum perspective?
Not quantum, but just a Wolfram physics project in general. Like Sandra, can you show that Shepardian causal graphs again?
Yeah. Sorry, I shouldn't give them away.
Yeah. I keep bringing it
Yeah.
back. Does it have because these
you want-
graphs? Yeah, I just want to comment on those graphs a little bit. I think like the relationship between these graphs and the actual physics project zoo of graphs that we have is these things are very similar to the token event graphs. Like whenever you talk about entities, like having this synchronous relationship between them in order to cause some effect. It's basically in our language would be there are some tokens that can be rewritten by applying some update event, right? So that's like entities producing a new entity, like X, like I and Z, Y and Z producing A. It's like some rule being applied to it, producing an event, right? That makes a new entity. So in a way, these arrows are not the causal relationship. It's like a structural relationship, that the thing that we actually usually call like a hypergraph edge. They just tie together in a spatial relationship. So two entities are tied together so that you can rewrite them and produce a new one. And in a way, events are in these causal graphs are implicit. So it's like they're not shown how the actual events been producing a new entity. So now it's like a purified token event graph without events. Something that shows all the relationship between tokens in the evolution of the system. Something like that. If it makes sense. Just my 2 cents.
That's really interesting, Nick. Thank you. I'm gonna look into that. Yeah, because she really zooms in and looks at like you say, like individual tokens. Yeah, which why she thinks that what other people have done, when they're zooming out and they're just looking at all these sequences, that she thinks one gets a misleading picture of nature, because that actually these sequences, if you zoom in on them, you find that they consist of these mutual and synchronous interactions. So it really is actually zooming in at the token level.
I have a question about the history and like the timelines of things here. So at the time when she was thinking about these things, had quantum mechanics been established or not yet? Is that no?
So she wrote this is in 1824, so it was still the Newtonian time, but there was like newer, like they were building on Newton's physics with, like, we have the discovery of, or like the more like the refining of the conservation of energy and also mass in chemistry. So there was a lot happening that time, but quantum, from my understanding, didn't come really into the early, like another 100 years, like early 20th century is my understanding.
And was there any mention or that she had some thinking about maybe alternative potential things happening simultaneously, like let's call it a multiverse kind of situation where, okay, fine, you have A and B that has some synchronous action, but in an alternate universe or at the same time, it could also be that B and C had the interaction, and there's like ambiguity between maybe what happened at the same time. Was that something that she potentially thought about?
No, she doesn't.
Yeah.
She doesn't write about that. Because it seems like, well, when I was expressing this with the multi-way system, it seems like her view it entails that really, if one simultaneous interaction happens, that automatically excludes other interactions, at least involving those entities.
Yeah.
But of course, you could have like if they're like different objects that are like parallel, like synchronous, but not involving the same objects, I think. Yeah, that's not something she was thinking about.
Yeah, it's very interesting to understand this perspective and kind of like working with this definition of causality, especially when it becomes tricky in the quantum case. Yeah, it's a nice mental exploration for sure.
That's really interesting. Thank you.
Great. So what is the next steps in terms of continuing what you've started here? Have you got thoughts on like where you'll take this research further?
So, the plan is with my mentors at the winter school, so with Hatem and Xerxes, we're gonna write a paper together about these causal graphs where like so in my dissertation, I'm just describing Shepard's view and writing about the history and philosophy of it. There's nothing like formal like and computational in it. So what we're gonna do in the paper is do that like formal part. So like express Shepard's idea or like Shepard inspired ideas connected to like the physics project and they have some ideas about to like express this in like mathematically. I think so. That's the next project is to kind of like take Shepard or like Shepard like ideas and see what like happens when we look at them more formally, like what I started to do at the winter school. Yes, I look forward to that and seeing where that goes.
Yeah, that'll be great. I can't wait to read the paper when it's out.
Thank you. I look forward to hearing what you think about it.
Cool. Any questions or comments in chat, Dugan?
Yeah, we have Jacopo asking in the physics project or in causal set theory, each node of a causal graph is an event. Meanwhile, are you proposing to consider causal relationships between entities? That is to say, the nodes in these graphs, are they entities or are they events between entities?
Must be the entities because and then the arrows between, so like X and Y, the nodes, so they're like the entities, so they're like two forces, for example, or two atoms, right? And then the arrows, that's like the event, that's what like the happening of like that they're mutually interacting, and then that creates the effect. That so yeah, does that
Okay, yeah,
make sense?
yeah. So yeah, there's I guess Nick could also speak to this, but there are different types of graphs, or like token graphs, then token event graphs, or just event graphs. So this is, you have the entities and then as the nodes, and then the events as nodes aren't shown, but the events are implicitly implied. They're implicit with the causal relationships of the edges.
Yeah, that's how I'm thinking about it.
Yeah, like having just a relationship between entities is like having just a structural possibility for an event happening. It's like in the physics project case, right? There doesn't have to be an actual rewriting event happening before. It's just specify that those atoms, vertices are connected, they are in relationship, but it doesn't actually say that there's actually some eventing and update happening. They're just together. So that's why it's a, yeah, it's hard to call it causal in our case because it doesn't actually causing anything if there's no rule being applied to it, right? It's just being structured together.
James, you're muted.
I was saying it's maybe like a meta rule or like a policy or something.
Well, if you're gonna call a hypergraph H a meta rule, then yeah, it's like you just a way of structuring your atoms of space vertices together. It's kind of meta rule, just structural rule.
Right. Thomas
It's a
Murph.
clear. Sorry.
Go ahead.
I was just gonna ask, do you think is a clear way to express what I've been described, or is there anyone who thinks like that would be a clearer way to to
I would love to see the category theory interpretation of this. Do you think category theory and causal set theory work well together, or is it kind of quite different? Like, or maybe Dugan also knows.
No, I wouldn't bring
the book.
category theory into it yet.
Okay,
It
okay.
might make us add a little bit more abstract nonsense.
Yeah.
Well, but probably.
But it is sort of the same thing. I mean, category theory, you have like objects or quantities, and they're passing logically through different apparatuses that produce, that mutate them.
Yeah, I think that's what Nick is saying. Is like, even just a single category brings a lot of additional stuff with it that might be too many tools than what's needed in kind of this very simplistic view that you have right now. So you adding too much complexity all at once to something that
You
might
have
not
to
need it.
introduce more, like an additional terminology, maybe like the call and the relationship between entities, like some kind of monoidal product. And there you go, you have a monoidal category, and then you have to describe your
Yeah.
events, morphism between them, right? Whether
Yeah.
they're composable or not, maybe form different kind of categories from that. I don't know,
Yeah.
but you can do it. But it's just going to be describing the same thing with a different terminology.
So causal set theory is probably the closest to what might have some useful tools here, right? I haven't looked into that much, but it sounds about right. And also the types of diagrams that theory produces looks like it could be useful. Maybe that's something Sandra can look into and report back.
Yeah, definitely.
It's definitely very relevant to the physics project, that's for sure.
One more question from chat. Thomas Murph asks, assuming two causes can have multiple effects, say 3, that is to say you have 2 causes, cause 1 and cause 2, and out from that you have like 3 effects. Is that possible? And is it also possible for those effects to interact and cause subsequent effects? Like, 2 causes come in and 2 effects pop out, but those effects make a 3rd effect.
Why not? Seems plausible, yeah.
Yeah, I guess
Yeah.
the effects could convert into causes.
Subsequent events.
So like if that one you get like really big effect, like really big causes, like wouldn't this be sort of like thinking like instead of like one billiard ball hitting another, it's like you imagine like multiple billiard balls are all transferring momentum and then those go on to later maybe give momentum to other billiard balls. Is that kind of the case?
Yeah, I would say so. I mean, yeah, because when you start a pool game, like you set them all up, and then you hit the cue ball to break them, and so they all go scattering, and there's a bunch of like little effects that happen in between. And that's just one example with billiard balls. I mean, the other thing that comes to mind is sort of nuclear physics, where you have like a neutron coming into like this uranium atom, and it produces 2 smaller like nuclei coming out of that, plus some other like radiation, like a neutron pops out, or several neutrons pop out, and an electron, maybe some other side effects like beta decay or photons popping out of that. So you have like one cause and a collision of two things, and then out of that comes like a bunch of stuff. Or in the case of Feynman diagrams, you have a whole zoo of like different possibilities.
Last question from my side. Did Shepard discuss the role of the observer at any point in thinking about this stuff?
Very easy question. So actually the last chapter of my dissertation is about how our view of causation relates to how we think about perception. So this is something Shepard was really interested in. It was sort of on a main interest was that she thought that if one thinks about causation in her way, it completely changes how we think about perception, like how when we observe the world, how we interact with it. And so in brief summary, like one of her like central claims is that she thinks like every time we observe something, we change what we observe. And this is because of the reciprocal nature of causal interaction. So it's not just like she thinks like when we're like when I'm looking at the screen, it's not just like the screen that's affecting me and like causing this perception. I am also like in return affecting what I'm seeing, like the how the screen. And here I think there could also be some interesting parallels to like modern physics about like observer theory. And I think she's like ahead of her time.
Yeah, and sorry, what era was that again? What sort of date range was that?
So she's 1777 to 1847. She published in the 20s, in the 1820s.
Okay, because I'm just looking here. The first double slit experiment. Yeah, first double slit experiment was 1801, apparently.
Oh,
Showing the wave behavior of visible light. So there might have been some of this interesting quantum experimentation ideas starting to float around, starting from that period potentially.
I doubt it was like quantum related. It's just like wave mechanics.
Yeah,
I don't think they were talking too much about observers at that time.
Okay, so that was just wave particle duality more than it was observer dependence of when there was interference or when there was not interference. That maybe came later.
Yeah, pretty much. They were all Newtonian at this point.
Okay.
It's just a background space. Yeah.
Yeah, it's interesting to look at the history of these things and then understand how these ideas were influenced by what was discovered over time. Great. Okay, thanks so much for that, Sandra. We look forward to further work in this direction.
so much for having me and for all the comments. This was really, really helpful.
Great.
Great. Thanks for everyone for tuning in. See you again next time.
You all take care.